Alrighty. So here we have a big truck and a small car. In this head-on collision, which one's going to experience the larger force? Hopefully, based on the thought puzzle that we started out with, we can all get the correct answer. Colby, what's the correct answer? Both the same. Why? You can either say forces come in pairs, or does anybody know which of Newton's laws that is? Okay. So you can either say Newton's third, or you can say forces come in pairs. The magnitude of the force between them will be the same. Okay. So then why is it that the car and driver are almost always worse off as a result of this collision? How would less mass change things? Sorry? Okay, so let's go like this. Force truck equals force car. That's Newton's third right there. By the way, what that also is going to mean is because they're in the same collision, the time is going to be the same for them. That also means if I put a delta t and a delta t there, the impulse, the change in momentum, they're going to be equal but opposite. Why would they be opposite? Because one's going forwards and one's going backwards, but they'll have the same magnitude. Okay, anyways, F equals what? Which one has the bigger mass, Trayson, truck or car? So I'm going to write it like this. Big mass truck, small acceleration, small mass car, big acceleration. And what I've taught you is what does damage in an accident? Not force, not velocity, it's acceleration. It's all about acceleration. I'm going to give you a term, a closed system. A closed system is one that is cut off from the outside world. That means there are no outside F applieds coming from off the page, no net external forces. Some examples would be frictionless surfaces. If it's completely frictionless, ice technically has a tiny bit of friction, but Declan will imagine it's got no friction. Systems in deep intergalactic space where there's no planets, those are frictionless. Those are nice closed systems. There's no gravity, there's no external forces there. Systems floating on water, water is nearly frictionless if there's no waves. So if you have flat water, it's nearly frictionless. Any of you that have ever had to move a boat, for example, you can move a really heavy boat on water just by applying a gentle force. It'll slowly accelerate and you can pivot it or move it along the dock pretty easily. Rolling objects as well. You're not going to need to memorize those. I'm just telling you those as examples so I can use them in the next few lessons. For a collision in a closed system, there's nothing pushing from outside. The contact forces are governed by Newton's third law. Forces come in pairs. So forces are equal but opposite. Since they're opposite, I'd probably let one way be positive and one way be negative. This means that momentum change, impulse, is equal and opposite. Why? Well, if the force of object 1 is negative, the force of object 2 equal and opposite. And if they're in the same collision, they must by definition be using the same amount of time. So I'll just multiply both sides by delta time and I get the definition of impulse, the change in momentum, except one's positive, one's negative. What that means is in a collision, if one object gains 1,000 kilogram meters per second, the other object what? Lost 1,000 kilogram meters per second. Yes. So if the car loses 20 units of momentum, what happens to the truck? It gains 20 units. Whatever units you're using. Metric, we use kilogram meters per second, but however you're measuring momentum. And this brings us to actually a fundamental law of the universe. Because momentum is equal and opposite, the momentum for the system is not gained or lost. It's simply transferred from one object to another. We have a phrase for this. We say, quote, you don't need to write this down, it's coming up on the next line, but we say momentum is conserved. If you're analyzing a collision, the amount of momentum you start with will always equal the amount of momentum you finish with, which means you can often figure out missing velocities. Yeah, turn the page. Wait a minute, Mr. Dueck. If conditions are such that the car and truck end up at rest after this collision, so here we have a truck and a car hitting head on, and they come to a dead stop, how can we say that we haven't lost momentum? It's a good question. If everything comes to a stop, Nicole, what's my momentum exactly as a number? Why? Because momentum is what times what? Mass times, it's on your formula sheet, P equals. Yeah. So if all of the velocities are zero at the end, what was my initial momentum? Zero. Okay. So I'm going to say this. That's my initial momentum. What letter are we using for momentum? What's our abbrev? That's going to be momentum of the truck and momentum of the car. Nicole, how do I calculate momentum? You told me 30 seconds ago. Yep. So it's going to be mass of the truck, velocity of the truck, plus mass of the car, velocity of the car. Juno's nodding. He sees where I'm going, I think. Juno, let's see. What's the mass of the truck as a number? What's the velocity of the truck? What's the mass of the car as a number? And be very careful. I should have put vector signs above these V's, by the way, and I should have put vector signs above these P's to remind myself to pay attention to direction. What's the velocity of the car? Not 24. Negative 24. And if you type that into your calculator, do you know what you get? You get zero. Momentum was conserved. It just so happens that because one was going positive and one was going negative, before the collision, your total momentum was zero. After the collision, your total momentum still zero. The law of conservation momentum says this. In any collision or explosion in a closed system, again, what do I mean by a closed system? There's no other outside forces acting on it. Somebody doesn't come from off the page and start pushing. Momentum is, here's your magic word of the day, conserved. In science, if something is conserved, what we mean is the amount you started with will be the amount you ended with. If you're in chemistry, you've probably learned conservation of mass during a chemical reaction. Mass can't vanish. Well, in physics, we have conservation, Juliana, of momentum. This means that momentum is not created, it's not destroyed, it's only transferred, I'm going to underline that word, from one object to another. We are going to have to pay attention to directions. I can write the law of conservation of momentum in several ways. First way, I can write it in English. The total initial momentum of a system equals the total final momentum of a system. You've had me for a year. Do you think I'm ever going to write it out in English without abbreviating? No, but you can. You can write it as, oh, what letter are we using for momentum, Nicole? P of object 1 initial plus P of object 2 initial, this would be if two objects are colliding, has to equal P of object 1 final plus P of object 2 final. Got no problem with that. Those of you that are in pre-calc 12, you may have seen this weird sigma. What does sigma mean? What's it an abbreviation for? Anybody remember or know? Okay. It means sum of or total. The total momentum that you start with, initial, is going to equal the total momentum that you finish with, final. I think, is that the version I put on your formula sheet? Where is it? The law of conservation of momentum. The total momentum before equals the total momentum after. Why did I go with that one? It's the least amount of writing. You know I'm lazy but organized. And also, it lets me bring out a Greek letter, which makes my little math nerd heart go pitter-pat. If you take that and you expand it, momentum is what times what? So it's really mass 1 V1 initial plus mass 2 V2 initial equals mass 1 V1 final plus mass 2 V2 final. That's the law of conservation of momentum expanded. If you want to, you could add that one to your green sheet. I'm going to say hold off for a couple of days. You might not need to. Okay? When do we use the law of conservation of momentum? When there's a collision or an explosion. When do we use the law of conservation of momentum? When there's a collision or an explosion. Here's my dumb joke. Oh, by the way, how will I abbreviate conservation of momentum going forward? Anyone figure it out? C of M. Okay. We use it when there's a jeune. Ooh, I heard a phone go off. Made a little beep. Sounded like it was coming from back there. No? Okay. Keep your ears up for the Timbits. There's a lovely example of conservation of momentum. It's something called a Newton's cradle. So Newton's cradle, a nice little toy, kind of fun to play with, but a nice example of conservation of momentum. Let's do some together. You ready? Example 5. All right. Kevin L., what does example 5 say? Find the, and then in brackets, let's let right be positive and left be, just so that we have some kind of consistency. And this first one I've done not as word problems, but as pictures. If this was a word problem, it would say this: car A is traveling to the right or forwards at 10 meters per second. It collides with car B, who is traveling backwards or to the left at 2 meters per second. After the collision, car B is moving forwards at 4 meters per second. How fast is car A moving after the collision? And the next lesson will be full-on word problems. But is there a collision? This is a job for conservation of momentum. Okay. What am I going to write first? I'm going to write the law of conservation of momentum, and I'm going to write it in the shortest way possible. Don't write this down. Look up. When you write a sigma, the Greek letter, it's supposed to look like that if you write it slowly and neatly. But most of us, when we're writing it fast, we just write it like a capital M on its side. The sum of all the initial momentum, write that down, equals the sum of all the final momentum. I write that down as kind of okay, I know where I'm going with this. Okay. Kevin, momentum is what times what? Okay, that's one you probably all want to commit to memory, even though it's on your formula sheet. All right. Before the collision, what's moving? Car A, car B, both, or neither? Were they stuck together before the collision or separate? So you ready? I'm going to go like this. Mass of car A, velocity of car A initial, and mass of car B, velocity of car B initial. Yes? That's the momentum we started with. Is that okay? Bam! They collide. After the collision, what's moving? Car A, car B, both or neither? Stuck together or separate? Say separate. How do I know if they're stuck together? If it's a word problem, the question will say after the collision they stick together. In our diagrams, oh, did I miss a stuck together? There was a stuck together. Oh, there. Those ones are going to be stuck together because their bumpers stuck together. Okay, let's go back here. So we're going to have this. Mass of car A, velocity of car A final, plus mass of car B, velocity of car B final. And I'm putting the vector signs on the velocities to what? Remind myself I better pay attention to direction. I better let one way be positive and one way be negative. Okay. What are we trying to find? So, you know what? I'm going to put a dot right there. Now, I got to be honest. This is around where my love of formula manipulation starts to reach its tipping point. I would have no problem if you just went 1,000 times 10 and put that number right there. And if you went 2,000 times that, put that number right there. If you went 2,000 times, put that number right there, and just got the solved it. I am going to get the VA by itself, though, algebraically, because that's what I do. I like doing everything in one line on my calculator. So, Kevin, we can do this. What side is the VA on, left side or right side? Left side's going to drop down like a domino. But I'm not going to drop my equal sign yet. Then what? We said we always do our adding and subtracting next because it's reverse bed mass. I need to move this over. What's this doing to the VA? How will I move it over? So I've taken care of that. Now I need to take care of the M. What's the MA doing to the VA final? So, and then if you don't mind, Kevin, I'm going to put the VA final over here by itself on the left because that's where we're used to seeing stuff. Yeah. And again, if you want to start plugging in numbers sooner than I am and start solving, I'm fine with that. But now let's go to numbers. So I've scrolled way down, Kevin. You're going to have to help me here. What was the mass of car A? Sorry? Car A is 1,000 kilograms? Is that right? Okay. What was the initial velocity of car A? What was the mass of car B? 2,000? What was the initial velocity of car B? Be very careful. No. Be very careful. You have to pay attention to directions now. Why is it -2? Look at the picture. It's going backwards. Yes? And then minus mass of car B, 2,000. What was the final velocity of car B? Positive or negative? Okay. All over car A, which was 1,000. What do you get? Let's see. Brackets around the top, or use your fancy schmancy fraction button. I get -2. Is that correct? What's the negative telling me after the collision? Which way was car A traveling? Yeah, so it looks like what happened is these two cars ran into each other. Car B bounced forwards, car A bounced backwards. They bounced off each other. I'm going to write -2 meters per second or 2 meters per second left. I'd take either of those. That's the law of conservation of momentum. I often just write this down whenever I see a collision to remind myself what I'm doing. Then I break it down to before the collision, what's moving. Each of those will have a mass and the velocity. After the collision, what's moving. Each of those will have a mass and velocity. And then, Colby, I solve for whatever I need to solve for. Let's do a couple more. B. Colby, what has a question mark next to it in the picture? I guess we're going to find the incoming speed of car A. Um, car B. Now, if you wanted to, Kevin, to avoid making that silly mistake, what you could do is you could label that one as negative and this one as negative right away. Colby, is there a collision? This is a job for conservation of momentum. So, the sum of all the momentum we start with has to equal the sum of all the momentum we finish with. Momentum is what times what from your formula sheet? MV. So we're going to go mass times velocity. Oh, before the collision, what's moving? Car A, car B, both or neither? Okay. Were they stuck together before the collision or separate? Now, if they were stuck together, I would just put the masses in brackets times a single velocity, but we'll get to that. So you said momentum is what times what? Mass times velocity. Colby, what am I going to write then for the before? It's going to be mass of car A, what? Velocity of car A initial, and I'll make a little mental note. That's what I'm trying to find. Plus what? Initial? Yes? Wham! They collide. After the collision, both moving and separate. Yes? So I'm going to have mass of car A VB final. Mass of car, oh, sorry, VB, Mr. Dueck, VA final. And mass of car, geez, Dueck, B, VB final. What am I trying to get by itself? What is the question mark next to it? Which one, final or initial? It's on the left-hand side, so what side's going to drop down like a domino? The entire? Yeah. First thing I'm going to do is go kathunk MAVA final plus MBVB final. Then what, Colby? I need to move this over. It's timesing the VA? How do I know? Plus sign. Yeah, I think I talked about breadcrumbs like Hansel and Gretel. It'll tell you. Minus mass B V B initial. Now so I've taken care of that. I kind of in my mind, I've crossed that out in my mind. I don't know if I'd cross it out actually, but in my mind, I need to take care of the M A. What's it doing to the V? So that's going to be VA initial. I've scrolled down, Colby. You're going to have to give me the numbers. So here we go. Mass A. Final velocity of car A. Mass B. Oh, -2. Mass, good catch, by the way. Mass B. Final velocity of car B. -2,000. Initial velocity of car B. Divided by mass A, which was 1,000. How fast was car A coming in? All of you want to be getting to your calculators. All of you want to be practicing typing these in. I'm going to need brackets around the top. (1,000 times -2 plus 2,000 times 4 minus 2,000 times -3 divided by 12? Yes? So if we're visualizing what happened here, car A, smaller car coming in faster at 12 meters per second, car B, heavier car going backwards at 3 meters per second. They collide, car B ends up going forwards, car A ends up going backwards, but momentum was conserved. Whatever momentum one car lost, the other one gained. Couple more, we're done. Here's an example of where one stuck together. Uh, ooh, okay. Ben, what are they asking me to find? What has a question mark next to it? Go find it in the picture. Initial or final? Okay, right? There it is. If I gave this to you as a word problem, I would say something like car A is traveling forwards at an unknown speed. Car A has a mass of 2,000 kilograms. It collides with a 4,000 kilogram car traveling backwards at 3 meters per second. After the collision, they stick together and they move off forwards at 5 meters per second. How fast was car A traveling at the beginning? All right. Is there a collision? This is a job for conservation of momentum. The sum of the momentum we start with equals the sum of the momentum we finish with. Momentum is what times what? Times. So I'm going to remember that before the collision, what's moving car A, car B, both or neither? Stuck together or separate before the collision? So I'm going to have mass of car A, velocity of car A coming in, mass of car B, velocity of car B coming in, initial. They collide. Okay. How will I show stuck together? Bracket MA plus MB V final. They stuck together, so they must be traveling at the same velocity. I've scrolled down. What were we trying to find? Right there? Good. Get that by itself. What side is it on? What side's going to drop down like a domino? Yep. Bracket MA plus MB close bracket VF. Then what? Then what? Well done. Yep. And that's going to be leaving behind VA initial all on its own. Um, talk to me, Ben. What are my numbers? What was mass A? Mass B? Final velocity? Mass B, you said was 4,000. Initial velocity of mass B? I was going backwards. -3. All over 2,000. This is one all of you should really practice typing into your calculator. This is about as complicated as it's going to get. Grayson, do you have the fancy schmancy fraction? Oh, okay, fine. Those of us that don't, I've got to put a big bracket around the top at the beginning and then a second open bracket, 2,000 plus 4.
Mr. Dueck, why couldn't I just go add it together in my head 6,000?
Yeah, if it works evenly, but if it's yucky, you might not be able to. Times 5 minus 4,000 times -3, close off the top, divided by 2,000. I think that's right. 21? Is that right, or am I wrong? 21? Okay. Car A was coming in pretty fast. I think we have one more. Yeah, one more, and we're done. I don't know if you did this when you were little kids with your very first bicycle, but when I grew up near where I live, there was a park that had a nice grassy hill. And so with our bikes, we used to do, we called it ghost riding. You would start on your bike down the hill, you would jump off, run alongside your bike for as long as you could while it kept going straight, and then the game was to see if you could jump back on. So we're kind of doing something here. This isn't a collision, this is an explosion. Really? What do I mean by an explosion? I don't really mean something went boom. What I mean is one object came apart. One object, two objects. Regardless, this is a jeune. This is a job for conservation of momentum. So, okay, I got this. Um, the sum of all the momentum that we start with equals the sum of all the momentum we finished with. Paul, what are they asking me to find here? Of? I guess they're using B for bike, R for runner. Okay, that makes sense to me. Yeah, pick smart letters. Alrighty. Well, before the explosion, what was moving? The bike, the runner, both, or neither? Stuck together or separate? How will I show stuck together? I'm going to go mass runner plus mass bike, the initial.
Whoa!
Then what? Oh, yep. No, I agree with you. VR final and which one of these are they asking us to get by itself or to find? Okay, I can do this. What's going to drop down like a domino? The whole left side. Then what? And then if you don't mind, I'm going to put the VB final here. Now, before we do the math, okay? How fast was the runner and the bike moving before the collision? So I'm going to show you some error checks so you can kind of make some predictions, Trace, and look up. How fast was the bike and rider moving before the collision? 5. How fast is the runner moving after the explosion? Did the runner gain momentum or lose momentum? Be obvious. Lost. So the bike must have gained because momentum is conserved. I can tell you right now, this answer should be more than 5. Whatever I type, I can tell you the bike must have sped. By the way, if you ever try this with your bike, yeah, actually, when you hop off of it, the bike will pick up some speed if you've slowed down. Just saying. What was the mass of the rider? Mass of the bike? The initial? Minus 20. No, not 20. Rider, Mr. Dueck. Minus 60 V final of the rider. All over mass of the bike. So I'm telling you, since the rider lost momentum, the bike gained momentum. And you should get an answer bigger than 5. Hope. 14? Anybody else? That is the law of conservation of momentum. The momentum you start with equals the momentum you finish with. And Juliana, it's up to you how you want to set these up. You have to at least think this. And honestly, on a test, I usually give a half mark or 1 mark if I see that, because it lets me know, oh, at least I knew it was a conservation of momentum question. I would advise not going to numbers right away. I would advise kind of writing it out with symbols, and then you can decide, do you want to rewrite the equation, Juliana, or do you want to stick your numbers in on this line and actually just solve it like a regular equation? This is about where the equations are getting complicated enough where I say, if you want to stick the numbers in first, go ahead. It's really up to you. What's your homework? Your homework is the take-home quiz, but you can also try number 1, number 2. Number 2 is just conceptual. Number 1 is also mostly conceptual. Number 3 is still conceptual. 4 is good. And now we're going to get into some Calvin and Hobbes. So you can try number 5. You can try number 6. So yeah, all 6 questions. But you'll get time to work on this next class after we mark the take-home quiz as well. Pause the video.